Karori. Now, the content in this lesson is alkynes. So, we've just like we have mentioned when we are dealing with alkanes and alkenes, alkynes are also is that class of hydrocarbons, which is differentiated between from alkenes and alkenes by the presence of a carbon-to-carbon triple bond. So for a compound to qualify to be defined as an alkyne, it must have at least one carbon-to-carbon triple bond. And you realize, just like we mentioned when we are talking about alkenes, when you have a double bond or a triple bond, that bond goes in eliminating the hydrogens that would have been bonded to the carbon. Because the bonds are bonding to themselves. In that case, the more the number of bonds between carbons, the lesser the hydrogens. And in that case, the general molecular formula for alkynes is CnH2n minus 2. Whereas we had seen for alkenes, that is straight chain alkenes, it is CnH2n. For straight chain alkynes, the general molecular formula where you have only one triple bond is CnH2n minus 2, where N can be 2, 3, so there is no 1 in this case because you cannot have a triple bond where there are no two carbons. So now, earlier when we were looking at hybridization, we had mentioned that for a triple bond to occur, then the type of hybridization is an sp1 hybridization, where we have two sp hybrid orbitals and two p orbitals. Sp being sigma forming orbitals, while pi being p being pi forming orbitals. In that case, all the pi orbitals in alkynes are situated in the position of the double bond, and so the third bond is a sigma bond. So in an alkyne, we have two, in the triple bond, we have two pi bonds and one sigma bond. And the molecule is sp1 hybridized. Now, meaning that the carbon of an alkyne molecule can only be bonded to one extra sp bond to the next non-triple bond atom. And the geometry in alkynes is linear, as we saw in sp1 hybridization. Sources of alkynes, just like in alkanes, can be either occurring naturally but very rare, but usually through synthetic methods. They are prepared through synthetic methods. The triple bond is usually very unstable, and alkynes, unlike alkanes and alkenes, are rare in nature. Nomenclature of alkynes, that is the naming system. So having looked at nomenclature of alkenes and alkenes, you realize that the naming system is not much different. So generally, we name alkynes the same way we name alkenes, only that we replace the suffix ane for alkanes and ene for alkenes with the suffix yne in case of alkynes. And we also, where necessary, I note where necessary, because if the position can only be one, you need not name the position. But where necessary, where the position of the triple bond can differ, then you should also indicate the position of the triple bond. So the simplest of alkynes is one with two carbon bonds. So when they are bonded, the carbons are bonded. So if you have only two carbons, then it is an ethyne. and therefore the other elements are hydrogen. But then you can have other alkynes where one of the carbons is bonded to, or both of the carbons are bonded to alkyne, alkyl groups. And so in that case, for example, in this one, where one carbon is bonded to alkyl, the other, then we say that this is a terminal alkyne. So in naming, so the simplest, we use the prefix eth, then add the prefix eth, and then we use the suffix ine. So the simplest 2 carbon is ethyne. If it is 3, it is propyne. If it was 4, it would be butyne. But when now the position of the triple bond can change, then we need to indicate the position of the double bond. So if, for example, it is butyne and it has only 1 triple bond, then it can either be but1-ine or 1-butyne or but2-ine, indicating that if the double bond is the lowest carbon number is, the triple bond, the lowest carbon number is 3. Now, where you have substitutions, then you give the prefix of the substituents. That is, if, for example, it is methyl, like this one, you count from the triple bond position, but you have to indicate the substituent. For example, in this, the substitute is methyl group at position 3. So it becomes 3-methyl 1-butyne, or it can be 3-methyl but1-ine. So those both names can fit the IUPAC system, where IUPAC means the International Union of Pure and Applied Chemistry. So a number of examples. For example, if you look at example 2 here, the triple bond is at position 2, but at position 6 of the 7 carbon longest chain, you have a methyl group, so it becomes 6-methyl hept2-ine, or then you could also name it as 6-methyl 2-heptyne. So that is very similar to the nomenclature we gave to alkenes. So now, just like in alkenes, we can also have alkynes that have more than 1 triple bond. Although I must mention that because of such molecules would be very unstable because of the high instability of the triple bond, which is prone to attack by many other atoms. So if, for example, you have 2 triple bonds, then you add di to ine to indicate 2 triple bonds. For example, molecule with 2 butene with 2 triple bonds and 4 carbons will be can only be in position 1 and 3. That is 1,3-butadiene, meaning that you have 2 double bonds. You also have an example of 1,5-hexadiene, and so on. So you can have a situation where you have a triple bond and a double bond. That molecule becomes an alkyne, but the double bond takes preference to the triple bond, meaning that it is considered an alkene with a substituent with a position which has a triple bond. So in that case, when you are counting or when you are naming, you name it as an alkene with an attached triple bond at the position. So if, for example, it is an 8-carbon molecule like that, this one with a double bond and a triple bond, it is an octene with the double bond in position 1, oct1 in, and you say you give that also 6-ine, indicating that also at position 6 you have a triple bond. So what that one shows is that the preference is on the double bond. Again, other major functional groups are also considered as preferences over the triple bond. For example, if you have an OH group, which indicates an alcohol, as you study later, and then the OH group takes preference and the molecule is considered an alcohol with a triple bond at some position. So, for example, this molecule becomes 3-butane-1-ol, that indicating that we have given preference to the OH group. Physical properties of alkynes, they are similar, they are related to those of alkenes. The physical properties of alkynes are related to those of alkenes and alkenes. They are insoluble in polar solvents because, again, we don't have polar positions. They have low melting and boiling point. But you notice that alkynes are linear. If you only have a triple bond, those molecules are linear and may have better packing than alkenes and may have slightly higher melting and boiling point. Though their melting and boiling points can be related to those of alkanes. So carbon 1 to carbon 4 are gases, carbon 5 to 13 are liquids at room temperature, and carbon 13 and over are solids, meaning that they are solidifying at lower carbon numbers. So just like alkenes and alkanes, they have lower densities compared to water, due, of course, to weaker intermolecular bonds. So looking at chemical reactions of alkynes, we start with the addition of hydrogen. Just like we saw in alkenes, hydrogen can add to an alkyne at the position of the triple bond, just the same way it adds at the position of the double bond in alkenes when you have a metal catalyst. For example, platinum or other metal catalysts. So if the platinum catalyst is present, then the first thing is that the hydrogenation will react at the position of the triple bond, converting the alkyne into an alkene, and further hydrogenation, depending on the amount of hydrogen present, will result into a net product being an alkene. Now, the addition at the position of the triple bond will very much depend on the type of reagents and situations present. So, you know, when you form an alkene from an alkyne, we saw that alkenes exhibit geometric isomerism. So the type of geometric isomer that results in the addition of hydrogen or other groups very much depends on the prevailing chemical circumstance. So in the presence of sodium in ammonia, the resulting alkene, where possible, is a trans isomer, while in the presence of palladium as the metal catalyst, what we call Hydra catalyst, the resulting alkene is a cis isomer. So it is important to note that given a situation, then if you want a trans isomer, then you can modify your reagents so that the reaction takes place in the presence of ammonia and a metal catalyst. If you want a trans isomer, when you are preparing alkenes from alkynes, then you use Hydra catalyst. Now, reactions with halo acids. Halo acids are halogens, are acids where the anion is a halogen. Now, again, once you react an alkyne with a halo acid, the hydrogen will add at one carbon, and the anion, which is a halogen anion, will add at the other carbon. Now, meaning that one of the carbon will have higher number of hydrogen counts than the other. And generally, ordinarily, if the reaction is taking place without interfering situations like presence of peroxide, the second addition will now follow Markovnikov's rule, as we saw in the reaction of alkenes. So the second, the conversion now from a halogenal alkene will follow Markovnikov's rule, so that the hydrogen adds at the carbon, the hydrogen of the second halo acid molecule will add at the carbon bearing the higher number of hydrogens. However, in the presence of a peroxide, that addition will take place in the carbon having the lesser number of hydrogens, what is referred to as anti-Markovnikov's addition. So if an addition takes place following Markovnikov's rule, then we say that it is a Markovnikov addition. If it takes place contra to Markovnikov's rule, then we say that it is an anti-Markovnikov's addition. Now, in the addition of halogens, generally, this will take place again without the presence of sunlight, because of we say that the triple bond is highly reactive, and the addition will first of all form a 1-2 or positions or additions in positions following another, having halogen or a double bond containing halogen atoms in both carbons of the double bond. And the addition again will take place to break the double bond until you get up with an alkane with 4 atoms of the halogen attached to what would have been the carbon positions of the triple bond. For example, if you're adding bromine, the same can occur in the addition of chlorine. Now, hydration, that is the addition of water. Again, hydration can take place to alkynes in the presence of mercury sulfate, that is mercuric addition of water. And the result is that the water molecule acts as if it is a Bronsted-Lowry acid, so that the hydrogen adds to one of the carbons of the triple bond, and the OH group adds to the other. An OH group attached to an organic molecule results in formation of alcohol. So the resulting molecule is an alcohol, or an alkene alcohol, what we call an eno. Now, enos, where the OH group is attached to a double bond, have the capacity of undergoing dynamic equilibrium, where the hydrogen of the OH group is lost, so that it joins the next carbon and the double bond opens, so that the double bond moves from the carbon to carbon double bond to the carbon oxygen double bond in what would be referred to as a ketone. So this type of rapid equilibrium is what we call ketoenotautomerism. Then another type of reaction is the reaction of alkynes with alkyl magnesium halides, what are otherwise referred to as Grignard reagents, or alkyl lithium reagent. So that kind of a reaction ends up with the alkyl metal reagents disposing of the alkyl groups they are connected to, and themselves joining one of the terminal carbons. If this reaction would only take place in a terminal carbon of a triple bond. So the hydrogen is of the terminal carbon triple bond is displaced so that we form, for example, it was a Grignard reagent, we form a type of a Grignard reagent in which the metal is attached to a carbon having a triple bond. And the same would happen in the presence of lithium alkyl reagent in the presence of an alkyne. Ozonolysis is, as we said, in alkenes is the addition of ozone. So in ozonolysis, now unlike because the carbon, one of the carbon or the carbons are not bonded, are bonded either to one alkyl group or to a hydrogen. The result is generally the formation of two aldehydes. One, if it is a terminal alkyne, which is methanol, and the other one is a wrong aldehyde. So ozonolysis results in the formation of aldehydes, or what we call carbonyl compounds. Reactions of metal acetylides and alkynyl Grignard reagents and carbonyl compounds, that is aldehydes and ketones, are the ones that we refer to as carbonyl compounds. So carbonyl compounds will join in the presence of either what we formed earlier, a Grignard's reagents joined at the carbon having the triple bond, or a metal reagent, or a metal joined to the triple bond. If you react with a carbonyl compound, the carbonyl compound will join at the carbon bearing the carbonyl oxygen, so that it is converted into an alkoxide with a triple bond. That is where OHO group, of course, if the metal catalyst is replaced by hydrogen, then you end up with an alcohol. And if it is, now because the metal is there, if, for example, in this one, that one is what we call an alkoxide, in which you have a triple bond at the position where the carbonyl carbon joined the carbon of the carbon to carbon triple bond. Preparation of alkynes. You see that generally alkynes are not very commonly found in nature because of the very high instability of the carbon to carbon triple bond. You see that in alkenes we have a strong electron density in the carbon to carbon double bond. So in alkynes it is even a higher density and therefore very unstable. So usually alkynes are synthesized. And one of the way of synthesizing the simplest alkyne, that is ethane, is through the addition of calcium carbide with water in the laboratory. You end up with ethane and calcium hydroxide. You can also form alkynes through the dehydrohalogenation of alkyl halides. So if you have double dehydrohalogenation, if that is if you have two hydrogen atoms joined to adjacent carbon atoms, then a double dehydrohalogenation will result into an formation of alkynes, and this is possible in the presence of sodium amine as a catalyst. So you can also convert smaller alkynes to larger ones by joining sodium acetylides with primary alkyl halides. So the primary alkyl halides in the presence of sodium amine will react. First of all, the sodium metal we replace one of the hydrogens, the terminal hydrogen, and then the alkyl group in the alkyl halides will add itself, resulting into a longer alkyne. So lastly, we talk about qualitative tests of alkynes. Now, the test of qualitative tests of alkynes are generally the same qualitative tests you do to alkenes. So generally it is difficult without doing more of the test. But the tests can be able to help you differentiate between alkynes as unsaturated hydrocarbons from alkanes. So, for example, the decolorization of bromine water, so alkynes, just like alkenes, will decolorize bromine water by reacting with the bromine and removing it from the solution, and or a bromine in carbon tetrachloride. And this one will not help you to differentiate between alkynes and alkenes, but it will help you to differentiate alkynes and alkanes, and in that case it is helping you to identify existence of unsaturation. Bayer's test, that is, alkynes, just like alkenes, are also oxidized by oxidizing agents, for example, potassium permanganate, and in that case reducing the oxidizing agents and decolorizing the oxidizing agents. And again, that is one way of differentiating between the unsaturation in alkynes with alkanes. So again, in the presence of ammonical silver nitrate and ammonical silver nitrate, terminal alkynes will give a white precipitate when treated with these reagents. And this is because of the formation of organometallic triple-bonded compounds, where the metal in the solution joins to the position of the triple bond, and therefore giving the white precipitate. And this can differentiate between alkynes and alkenes. Now again, this test can also be able to differentiate between alkynes, which are terminal, and non-terminal alkynes, because whereas the non-terminal alkynes will give a white precipitate, terminal alkynes will give a brick-lead precipitate. So that generally brings to the end of the coverage on alkynes. Now we have questions, exercise questions. One, discuss how sp2-1 hybridization in ethine is formed, giving details about geometry and other properties. So that one is a question you can answer by considering the topic on alkynes and also considering hybridization. So explain the Markov-Finikov addition of an acid HX, that is a Blonstedt-Lowry acid, to an alkyne. Question 3, suggest 3 simple laboratory tests you use to distinguish between butane and butane. That is butane being an alkane and butane being an alkyne. So thank you. That is the end of lesson 4.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.